Welcome everyone, and thanks for tuning in to the third and final day of our 2021 Agricultural Faculty Academy webinar series and the Innovations in Surface Irrigation and Conveyance Systems webinar. We would like to take a quick moment to thank our sponsor Rainbird for helping make this event possible, and a quick moment for some housekeeping notes. I have muted everyone by default, so we won't be disrupted by latecomers. Please keep yourself muted throughout the presentation unless you have questions, as this will help minimize any background noise. During the presentation, if you do have questions, you can either ask verbally or via the chat box. I will be monitoring the chat box throughout the entire presentation. If you would like to ask questions verbally, please use the hand raise feature, and then I or our presenter will call on you. Without further ado, I would like to welcome Darren Fillmore with Swim System Ltd. Take it away, Darren.
Thank you, Nicole. Happy to be here this morning, folks, and share a few things I've prepared. I'll see if I can get my screen share back up. All right. Hopefully everybody's seeing the title screen here. First, I'd like to thank Irrigation Association for extending the invitation to present here today. Hope it turns out to be valuable for us all. As Nicole introduced, I am Darren Fillmore. A little update in my career path here. I'm working as an independent irrigation engineering consultant for now and serving as a part-time contract position for Swim Systems still. Also on that subject, as we're talking about innovations and technologies, I will be highlighting some solutions from various companies. I'm not employed by any of them, so don't consider it endorsement, just some examples of things that we are discussing. All right, first, our discussion format. Nicole mentioned a little bit about some of the tools available to us in Zoom. You know, I got a chance to look over the list of registered attendees, recognize some names there, good to reconnect with some folks, recognize the names of a lot of great institutions as well. So I'm under no impression that I'm the foremost expert on any of this. There's a lot of great knowledge among the attendees today, and I hope that I can just be the guy leading the discussion and we can have a good active discussion. That said, it can be a little tough to do that over Zoom. It'd be a lot easier if we were in a face-to-face meeting to get a lively discussion going. But I really think this conference is your conference, and the more information you can exchange, the better. And hopefully the few topics I prepared will help spur some of that discussion. But please don't be shy. Please use the microphone if you have it. Ask questions verbally. Type them in the chat box. Don't wait till the end unless you feel like you need to. Feel free to interrupt anytime. I can back up to a previous slide. If you don't think of your question until later, that's fine. I want to encourage as much participation as we can. If you came here for a lecture, you're going to be sorely disappointed. I'm not a lecturer. I think that you educators probably do a lot better job with that than I am. So I really do want to encourage a discussion. Of course, if y'all want to just be quiet and listen, lecture will be, and it'll be over pretty fast. So let's go over a little bit of what I want to discuss here. First, a little background on this topic. For those of you who have served on these conference planning committees, I imagine a number of you have, you know the amount of work that goes into them. So hats off to the folks who are serving on this committee and to the IA administrative staff for putting this together for us. I was contacted by a college friend, Evan Thompson from Nelson, who's on today. And really this topic, I have to say, wasn't my idea. He presented it to me and I really like it. So I want to give you a little bit of background as to why we wanted to talk about this today. So it seems like there are other areas in irrigation that get a lot more attention. Pressurized irrigation, soil moisture management, irrigation scheduling, some of those things that are funner to study perhaps and sexier. There's widgets you can design, hardware you can sell. I think probably those are the reasons they get a little more attention in my view. But I'd like to focus on some things that don't get as much attention. Surface irrigation, open channel conveyance being a couple of those. You'll see from the overview points there are a few things even outside of those topics that I want to bring up. And again, just as a hope to spur some conversation among us and exchange ideas among you folks. I'd love to learn from you and see you learn from each other. So we'll talk a little bit about where irrigation fits into the big ag picture, and hopefully get some feedback on how you folks think it works in your programs. Storage as well as kind of the precursor to conveyance. Then we'll get into the innovations and technologies in surface and conveyance, and talk about other tools as well. So foundations of agriculture, kind of the introductory topic slide. And this is really basic stuff. I don't present it because I have any impression that you folks don't understand it, merely to kind of set the stage for what we want to talk about, and like to hear your perspectives on where irrigation fits into agriculture and why your students are interested in it. So one aspect of agriculture is, of course, crop production. One of many aspects. If we look at agriculture as a whole, and especially sustainable agriculture, a lot of other items come up, such as society and environment and economies and so forth. But certainly crop production is a major part of agriculture. So we'll focus on that one. And then several foundations that underpin crop production. Big one, of course, is soil moisture management. In irrigated agriculture anyway, that's something we intend to manage. And then that overlaps salinity management and nutrient management. So those do have their own components, but also it's a little bit overlap with soil moisture management. Now, in this graphic here, I'm trying to depict that there are a lot of other foundational principles to crop production that we're not addressing. So little pyramids in the background are an attempt to show there's so many other things like pest management and variety selection and so on and so forth that we're not going to even come close to today. And the notion is here that soil moisture management is such a small part of the overall picture of what agriculture is. And the niche that we're in tends to be a small world. It's great to get folks interested in it, and especially folks who are studying to take up a career in irrigation. I'm really interested to hear what those folks are thinking and why they're interested in it now. So focusing on that center pyramid of soil moisture management, really, when we talk about soil moisture management, it's irrigation and drainage. Those are the primary tools we have to manage soil moisture, at least in irrigated ag. And we'll talk about some of the foundational principles beneath that. And again, some of these topics aren't necessarily directly under the field of irrigation in terms of study and practice, but they certainly are foundations that we need in order to be able to do irrigation. So I want to acknowledge those and hopefully get folks thinking about how they fit into their programs, and how your students might be able to branch off and find the niche that interests them the most. So water supply planning, obviously we can't irrigate without a water supply, and the planning of how to maintain and secure that water supply is in itself a fascinating field, and folks build their whole careers on water supply planning, especially in the arid parts of the world where there's a lot of demand for the water and not a lot of supplies. It can be a full-time job trying to secure those supplies and keep them available for users. And that gets into watershed and aquifer management. Obviously, in order to have a water supply, you need to understand, manage, and protect where that water supply is coming from. So that typically means a watershed or an aquifer. Again, not a real or a specific correlation to irrigation here. That's a little bit peripheral. Watershed science, folks who work in that might call themselves watershed scientists, hydrologists, and so forth. They might work for the Forest Service or the USGS, not necessarily directly in irrigation, but they still very much affect what we all do. Similar with aquifer management, your hydrogeologists, those sorts of folks who study groundwater may not be thinking of themselves as irrigation managers, but in a way they are. And then the final foundation, which really I think underpins all of this, is water policy. I bring that up because you may not acknowledge it or even think that's where you're going to be going with your career when you start out in irrigation. Tend to realize that it all comes back to that. You can't really get to the technical side of irrigation if somebody somewhere isn't handling the water policy well. A lot of folks find themselves gravitating toward that in their career. So I hope that your students get a little exposure to that through your programs and have the opportunity to start out there earlier in their careers if they want to. I want to pause here. Now we've gone through some of this background stuff and ask if there are any questions or comments. I'd like to hear from you folks about what you think of irrigation as the little niche that it is within the big picture of agriculture and how it fits into the work you do. Anybody care to comment? I'm assuming I'd hear if anybody were speaking, but I'm not sure.
Yeah, no comments yet.
Well, we got a quiet bunch. Might be a quick presentation, folks. Well, I'm looking for some feedback here. So another topic here that is kind of peripheral to irrigation, definitely a really important part of irrigation, but folks who work on water storage may not consider themselves irrigation experts. Might have civil engineers, of course, to designing dams and reservoirs or spreading basins like we see on the image on the right there for aquifer recharge. Water storage can be in large reservoirs that serve many users like we see with the Hoover Dam there. It can be small on-farm ponds or anywhere in between. So there's a lot of ways that water storage is important for irrigation. And of course, irrigation can be done without a whole lot of storage. It just makes it a lot easier when you have a little bit of buffer to help when things are unexpected, such as a rainstorm or heat wave, things like that. Okay, so finally getting into the topics we said we're going to discuss, conveyance and distribution. So I separate those. Some folks may not see the need to do that. Conveyance in my mind is your river systems and large canals that move water from its source and its storage points into the use areas where it can be distributed. So our distribution systems then become branching laterals, whether those are pipelined or open channel, that carry water to the points of use, delivery points. So that's the way I distinguish them. Again, with conveyance and distribution, there are a lot of different ways that you can get involved in that as a professional, a lot of different areas of practice. Some folks are a master of all of them. Some of them tend to focus on just one or the other through their career. So flow measurement is one that a lot of folks do get excited about, when I've had a chance to do a little bit of in my career. And we'll talk a little bit more about that one specifically. Hydraulic modeling, it can be a lot of fun too. Depends on the kind of hydraulic system you're talking about. It can be really complex. So as you can see in the little graphic I borrowed from Ayers there, that's a 3D model. Makes for a pretty picture. Designing channels and pipelines, another interesting component, does kind of cross over with hydraulic modeling and with the next topic of structure design. Again, the structure design, designing water measurement, water management structures, kind of gets over into the civil engineering side a little bit more. Some folks would gravitate to that. Indeed, a lot of folks I've worked with have been civil engineers who never really thought they'd be working in irrigation. It just happened to be the kind of structures they ended up designing. Estimating seepage losses, and then working on seepage interception or seepage prevention through channel lining and so forth. That's another interesting side of conveyance that you might not think about. It can be a big deal. In fact, if we back up to a previous slide here, that's the All-American Canal that goes along the southern border between California and Mexico. And you can see the sand dunes in the background. That was previously a highly permeable part of an earthline canal. And that was lined, a lot of you folks are probably familiar with that, but that was lined through a joint project with a number of water agencies, but one of the primary ones was San Diego County Water Authority and the Imperial Irrigation District. And they found a funding opportunity there to line that section of canal that seeped a lot of water into groundwater that was then lost across the international border. A great project, and really interesting from a construction standpoint too. You get a chance to look at some of the things they did to line that enormous canal. I think its capacity is 26,000 CFS or a little bit more. And they will line that while keeping it in service. Fantastic technologies there. Back to some of these other areas of practice. Automation design, we'll touch on that a little bit today. Tends to be another one of those areas that gets people excited and is fun to work on, and has some good applications both in the irrigation side on farms and on the distribution side. Operations optimization. So by operations, I mean operating the canals and laterals that tends to fall to ditch companies and irrigation districts and the like. And I have a lot of good folks, both in civil and irrigation backgrounds, working on that sort of thing. Evaporation estimation, and it crosses over with evapotranspiration estimation. Evaporating or estimating, what's coming off of these open channels and what the losses are, what's lost through phreatophytes and other uses before the water ever hits its point of delivery. And then operation and maintenance, another important component of managing and operating these canals is how they're operated, try to keep that operation optimal. Maintenance can be a significant challenge as well. Entire careers can be dedicated to that. Flow measurement technologies. So just an aside here, folks, you notice I'm not getting into any of the technical details, the theories or the equations or anything, really just getting through a broad overview of some of these topics. I imagine a lot of your curriculums already include these things. I just present them here as ideas of things I think would be useful from my perspective in industry. Obviously, I'm not in academia, but from industry, I think from an industry perspective, these are things that would be valuable for new graduates and folks who are furthering their education. So back to flow measurement technologies here, acoustic Doppler meters. I put a number of different types of examples there. In fact, the pictures on the side are mostly acoustic Dopplers. A lot of the ones on the market are single path. Usually they'll have one beam angled into the flow path, and the attempt there is to get an average of the velocity distribution profile by situating that beam in the right place in the profile. Another approach is the multi-path. Image on the bottom is one example of that from Sontec. They have several skew beams and the traditional forward-facing beam. And then also a vertical beam to catch the depth of water. So I believe it's 5 sensors in all. And those sorts of sensors are devices, I think, do a pretty good job of estimating when the profile is not typical. So if you were to just try to measure a profile with one beam that has a lot of variation across it, whether it's because of disturbances in the flow path upstream or downstream that you weren't counting on, or surface winds or other things like that, there are certainly good cases where you'd want to have a multi-path velocimeter to better profile that velocity. Horizontal beam, I think the third image from the top there is a horizontal one, side looker, what Sonotech calls theirs. Shoots across the channel from the side and profiles the velocity that way. Works pretty well for wider channels and for channels that are hard to access or that have movable bed forms. Bolt mounted, what we see in the top image, that can be dragged across a profile or along the flow path, and to try to profile better the depths and the velocities. Also, those can be situated on a buoy line and held static once the point of interest is determined. And weighting stream gauges, I imagine a lot of you folks are familiar with those. I don't have a photo of those, but the older ones that were used decades ago, the propeller type ones or the cup type ones, like the price meters, the pygmies, those are still in use in a lot of places. For the most part, the counting mechanisms are better than they used to be when you actually had to count audibly. They have data loggers on them now, but also they have a lot of opportunities to upgrade those to acoustic Doppler, electromagnetics, and other types of measurement technologies to estimate that velocity rather than the mechanical style.
Darren?
Ultrasonic transit time, it's typically a technology used similar to Doppler, but rather than looking for the frequency shift caused by the velocity of the water. That's another interesting area of study. Lasers and radars, those are a couple.
Darren, we just lost your shared screen.
Looks like I lost my connection there.
Oh,
Oh, the share's gone too?
Yep.
Yeah, I lost my connection there. My apologies. Okay, I think we should be back. Forward. All right. Back where we left off, I believe. So we're talking about, or at least I was talking about laser and radar measurement before I realized I was talking to myself. So laser and radar are both technologies that are deployed above the surface of the water. There's some significant advantages to that, especially when you're dealing in dirty water or salty water that can inhibit some of the measurements for the devices that you'd be placing in the water. Some do a better job than others of profiling the entire velocity profiles. I think radar, for instance, can only really pick up the surface, and you have to estimate how that varies from the rest of the profile. Laser, from what I'm told, can sample from within the depth profile, but can't say I have any experience with those ones. They're pretty pricey units. They were. Anybody have any particular experience with any of these devices or any questions about them? Feel free to raise your hand or just chime in by audio when you can. Hearing nothing, we'll move on to another flow measurement slide here. So a few more ways of measuring flow that tend to work in irrigation channels. First, impeller meters. I typically think of those as a pipeline solution as well. Your impellers or propeller meters, as they're sometimes called, fill a whole pipeline and fit almost snugly in a pipe so that you capture that whole velocity profile. When they're used in open channel, it can be like we talked about before with the weighting meters and the Price 01A style, or Another way is a lot of times the irrigation delivery will go through a culvert to pass under a farm road, and in that culvert they'll place a propeller meter, and they don't tend to be as large in relative to the total pipeline diameter as typical pipe meters. It's just a propeller that fits in very loosely in the culvert in the center part. And again, they're attempting to capture the velocity at that point and assume how the rest of the profile behaves. So there are some inherent inaccuracies with that. Hydraulic measurement structures. So those can be fun to design. They might get a lot of folks in academia who've had some experience with those. Flumes, weirs, submerged orifices. They do have their place in open channel measurement. They can also have some real challenges, particularly in areas that don't have a lot of elevation difference. You don't have room for any head loss from flumes or weirs. Now there are good designs that don't require a lot of head loss. Then you have to be able to measure a very small difference in head from upstream to downstream or mid-throat on some of these structures. So the photo there on the right is a laterally contracted flume, version of the long-throated flume that has an open bottom. Pretty similar to a broad-crested weir. A lot of you folks are probably familiar with those, and indeed with these as well. But it's essentially little broad-crested weirs that are built on the sides of the channel and only contract the sides. And one advantage I've found of those is they don't have quite the psychological perception of a dam that you hear from water users. You put a broad-crested weir in a farmer's ditch and they're going to tell you dammed off their ditch. Whether you tell them all day long that it'll still carry just as much flow, it just accelerates it through the throat, and it still looks like a dam, and it makes them uncomfortable. This open bottom gets past that, and also has a very practical advantage that it sluices out the sediments, whereas a broad-crested weir, even if you put a good-sized drain pipe in the bottom of it, you tend to get sediment and debris building up in front of it that has to be shoveled out. This is self-cleaning here. They also can be pretty successful in areas where you have low head available, but you do have to be able to measure that head difference with precision. So talk a little bit more about level measurement systems here. I also wanted to mention submerged orifices. So the top image there is one solution from Swim System that measures upstream, downstream, and gate position on a vertical sluice gate. So my apologies, you can't really see the whole gate there. We're just looking at the side of it, but that's a rectangular sluice gate that's raised up and down to control the orifice and manage deliveries from a main canal into a farm ditch. So that particular one uses wireless ultrasonic level sensors. They have their advantages. Of course, they're battery operated, so that can be a challenge sometimes as well. These ones were retrofitted with solar panels. You can kind of tell that, but the intention there is to measure the upstream water level, the level upstream of that gate before the contraction, and then the downstream water level. You can see the sensor a little bit in the gap between the vault cap and the gate there. Of course, that only matters if the gate is submerged, but often they are submerged, in especially these flat areas where you don't have a lot of head. And
Darren, I think your connection is coming in and out again.
then the gate position to my hotspot. If you folks will bear with me for a minute, I think I have a plan B that should prevent that. May lose connection here as I switch, so bear with me. Yeah, I think we're back online. Hopefully we didn't drop out, have to start over. So we're talking about submerged orifice measurement, and this particular solution that nothing particularly novel about it, but we're using ultrasonic level sensors to measure that upstream, downstream, and gate position. And the gate position sensor, you'll notice, does reflect off of 45. So it's a kind of an interesting application of that. Thank you, Nicole. I hadn't noticed that. Very good. So on to level measurement. We touched a little bit on ultrasonic level sensors. Those ones pictured there are wireless ones. They communicate to a gateway that you can mount a number of feet away, and works pretty well if you've got constraints such as right of way, or you'd have to bury conduit under a highway or things like that. There are also wired ultrasonic level sensors that do a great job, and you get away with a lot of the problems with radio connection and with batteries and so forth. The bottom picture shows wired ultrasonic level sensors over that flume there. And those also are great because they're non-contact. They stay out of the water. They do take a lot of abuse from the sun, depending on which area you're using them in, but they don't have to worry about, you don't have to worry about sediment and salt buildup and so forth on those. Laser range sensors, another way to capture water level from above without contacting the water. They have their pros and cons too. Some of these work better than others in a stilling well situation. We have had trouble with ultrasonics in smaller stilling wells. They have to be a fairly good sized stilling well to stay away from the sides and avoid echoes. Lasers don't suffer that. There can be some reflection problems. Of course, spiders love to get in stilling wells too and mess things up. Bubblers, air bubblers. That's, I believe, a technology that was born in the oil and gas industry, but if you haven't used those are pretty interesting and can be very accurate. So they have a very small compressor that's part of the above ground system that pushes a small bubble out of the line down below the surface, and the back pressure on that line is measured to calculate the depth of the fluid. Again, they use them in oil and gas. They work in very deep wells as well as some of the shallower things. Another advantage to those, and with any of these systems really, is when you're trying to measure a very small differential, like you see in the lower picture there, the flume, the difference from upstream to throat level is very small, and any error in that can be turned into a very large error in your measure estimate. So bubblers have the promise of being able to use the same compressor and the same pressure sensor, so that they eliminate any sensor bias. Whereas if you were to use two separate sensors, you might have a bias just from the error of one device to the next. They have their challenges too, of course. They can, there's more moving parts, of course, with the compressor and so forth. You do get a little more maintenance trouble sometimes. Floats in stilling wells, you can use string potentiometers or shaft encoders to track the movement of a pulley and float system. That's kind of a tried and true method. Seems to get rid of a lot of the problems that we see with some of these newfangled ones, and works real well again in a stilling well. You'll have a lot more problem with that if you try to use it directly in open water. Pressure transducers also have a place in measuring levels. They can have problems because they are submerged. They're not a non-contact thing. So sediment, especially finer silts and so forth, can block off the ports to those pressure transducers, and salt can crust them over. But with some maintenance, they're pretty good measurement technique as well. So moving on, any comments on level measurement or flow measurement at this point? Any folks have any experience with any of these things that you'd like to share? I hope you're all saving your comments for the end. Monitoring and automation. So we'll discuss monitoring and automation first from a conveyance and distribution perspective, and then get into how it looks on farm next. I hear a couple of examples on this slide of canal automation from different manufacturers here, large canals, and especially the one on the top there. So one of the challenges in managing a canal is just managing how the water moves across topography. So if it's a canal that covers a long distance or a lot of elevation change, there's going to be a number of check structures to control that drop. And those check structures are also an opportunity to store water, pond it up a little bit, and release it as needed. And then also pond it up for delivery to a lateral or even a water user. And then to control the flow rate through that check. So as with most of these automation mechanisms, there's opportunities to use these automated systems to either control the upstream level, the downstream level, or the flow rate. So different algorithms to do that, and different hardware works different or works better for some of those than others. So what we see on the upper image there, those are more like a sluice gate, drop leaf gate, and then below, excuse me, the top ones are drop leaf, the bottom ones are sluice gates, where a vertical gate that opens from the top. Both can be actuated and automated. Oops, sorry, we scrolled the wrong way there. All right. A little bit more about automation from a big picture perspective. Of course, credit to Rubicon Water for these images here, and also for some of the information. So the top image shows kind of a graphic of all the different places along the flow path from the watershed all the way to the root zone, where measurement and automation can help improve the way water is used. So there is this estimate from Rubicon that about 37% of the water that's actually diverted from storage actually makes it to benefit the crop. So it indicates there are a lot of losses along the way and a lot of room for improvement. So first, if we were to think about automation from the top down, there's room for automation within the watershed itself before water even makes it down to the rivers and reservoirs, just to measure what's there, to help control erosion, to give feedback to watershed scientists about what kind of things are going on in the watershed, whether it be erosion or contamination, just general hydrology, what's going on with the water here. Once it makes it to storage, a lot of effort can go into reservoir operation. I imagine a lot of you folks are familiar with that. But automation has a place there, whether it's just to monitor reservoir levels, to manage spillways, and to manage releases from the reservoir. A lot of that can be automated based on the management parameters that are desired. And then the conveyance from that dam down to where water hits a distribution system. Again, we just looked at the automated check structures on some main canals, automated lateral headings, do a lot of the same things where you'll want to measure, or rather control, flow rates or levels. And a lot of these technologies allow you to do that, usually through actuators on some sort of a gate device, be able to control the flow rate by changing the size of the orifice. As we get past the conveyance into the distribution system, a lot of the same things apply in the distribution. There's smaller canals, essentially the same thing. But you get into delivery gates then, where you're delivering water to farm users, and the requirements there come a little bit different. In a canal, you might want to hold this particular level, whereas in the farm ditch, the flow rate might be the more important component, especially if downstream in the ditch, that water is being pumped into a pressurized system, be it drip or sprinklers. Typically, those pressurized systems have a constant flow rate, and the users would really like to have a constant flow rate in their head gate as well. Not always possible, especially with varying conditions up and down a distribution system, but automation really helps steady that flow rate and give users a better opportunity to use that water to match their needs in the field. The lower image there shows, again, from Rubicon Water, actual data, I believe, from Oakdale Irrigation District in California, but what the canal level looked like prior to automation and after. So you see a lot of variation in the level, and their desire was to hold a constant level there to help them manage the flow rate in the canal better. And with automation, you see it cleaned that up quite a lot and gave them a lot better control of it. Couple of problems that tend to come up in automation systems. One is just mindset. Folks who've been operating canals manually for decades or even centuries, in some cases, a lot of history and how things are done, a lot of art to it, and there can be a fair deal of resistance when you start handing it over to computers and mechanical devices. Folks aren't comfortable with being replaced by a robot, and that can lead to just some resistance in adoption. And as some folks have said, it's difficult to make someone understand something that they don't perceive benefit from. They think it's going to harm them, and all of a sudden it's really hard to understand. And that's a real hurdle to get past. And then there's a social aspect to that too. If folks perceive that jobs are going to be replaced by machines, there may be some political pushback from that, labor unions and the like. What I've seen in reality is it just shifts the skill set that's needed. Instead of being somebody with a strong back to move checkboards in a canal, now we need somebody who can do troubleshooting and manage technical systems and hardware and so forth. And it can be the same people who were doing the manual labor before. They just need to be open to learning some new skills, and that's often very successful. Other challenges and criticisms of this sort of thing, automated structures in canals, is failure points. You know, if these canal gates or a check structure were to close when it needed to be open, you can imagine that you're going to have an overflow, and you could have significant flooding from that. And indeed, we've seen that happen. But the same is true of manual systems. You can have human error there. Indeed, a lot of the errors that we do see in automated systems come back to human error. An operator somewhere may have keyed in a value and struck an extra digit or something like that in a flow rate. That's not to say there aren't hardware errors as well, components that fail and things that break. That happens, and can happen both in manual systems and in automated ones. But it is a fear, especially when you're talking about shifting from one regime to another, that something's going to cause a catastrophic failure and significant economic damage. And we've seen it happen. So getting past the delivery point in the field itself, of course, there are a lot of opportunities for automation, measurement, and control with soil moisture measurement. A lot of folks are familiar with the different types of soil moisture. We might get into that too much, but you can talk about automation in the canal in the field to provide feedback to an irrigation system. So based on soil moisture, you may be able to move to the next set or turn valves on and off, that sort of thing, or even just notify an irrigator that it's time for him to manually assess the condition and change it. There are other kind of peripheral sides of automation, both in the conveyance, distribution, and on farm, such as modeling and scheduling and things that are necessary to be able to understand some of the hardware and understand the algorithms that control it. We'll get into a little bit more of that here. Just some slides here, again, courtesy of Rubicon Water, of some actual results. In this case, it was a spill structure at the end of the lateral that they replaced with an automatic device. The manual device on the left and the automated version on the right. A couple of things you notice is just how different it looks physically, but then in the bottom image, the amount of spill afterward. They had enough water in that downstream channel that certainly could have been used for other purposes. And then in the right, you see there's probably still enough to keep vegetation alive, but not the steady stream you saw before. So there's some water conservation to be had there. And then another side of it is just the steady level they're able to hold there. You see there are 2 delivery gates upstream of that spill structure, Waterman style gates. I would guess those tail ender irrigators there are happier with their deliveries after this installation because they have a steady pond to pull from. A couple of advantages there. So back to delivery from the distribution system to the on-farm. Here on this slide, we have 3 different examples of automation in the head ditch itself, or in the case of the one on the right is an alfalfa valve from a pipeline. A couple different manufacturers highlighted there, but all trying to achieve the same thing, and that is control in an automatic fashion the water as it leaves the head ditch and goes out into the field. So the one on the left there from Watch Technologies, you see they've actuated what is typical slide gate. Should have included a before picture on that, but those slide gates are ubiquitous throughout the Southwest on a trapezoidal farm ditch that just has a handle, and an irrigator has to pull that slide gate up and down to control the water through a little port in the side of the ditch. Imagine you folks are all familiar with those. Here they just put an actuator on it, and then there's feedback from soil moisture measurement in the field and control from user devices and so forth that allow them to move that gate up and down. It's a lot of different attempts at that over the years that I've seen, some more successful than others, but there can be some challenges to moving those slide gates, especially when they're burdened with a couple feet of water. Also, in the middle here is a different version. So you can see in that case that we don't have a slide gate. They have what Rubicon and the Australians call a bay gate. Much wider gate, opens up and lets a large flow rate out of that ditch, and there are reasons to do that. I hope we get a chance to discuss that a little bit. But also it is automated. You see with the control structure there to the right, you kind of make out the upstream level sensor on that system with the radiation shield over it. So the intention there is to control the flow rate through that. It's a leaf gate again, essentially, and be able to control what's going out into that section of the field, bay as they call it. And then finally, that blade valve is what Rubicon calls that, but it's an automation on the alfalfa valve, riser off a pipeline, often used to flood a field. That can be automated and controlled much the same as these other valves and gates can be. But it all depends on models and feedback from either from the users or from other sensors in the field. So look a little bit more at that. So surface irrigation, let's talk a little bit about the challenges of surface irrigation. I mentioned a little bit earlier that pressurized systems tend to get a little more of the attention when it comes to automation. The pressurized system, frankly, is a lot easier to automate. There's a lot less opportunity for user error in pressurized systems. Still plenty of opportunity for it, but less than in the surface irrigation. Seems to be more of a science and less of an art. Surface irrigation can be every bit as efficient as the most efficient pressurized systems, but it's harder to get there because there are, again, more opportunities for human intervention, and that can be beneficial or not. Also, you have factors, just limitations on flow rates, a lot of changes in soil texture throughout a field or for an irrigation set, a lot of challenges that make it difficult to manage surface irrigation and get the kind of efficiency that folks would like to see. So in those couple images you see there on the right, pretty common to have too much infiltration on the upstream side of surface irrigated field, especially if we're talking about wild flood or border check systems, even furrows, because there's just so much more intake opportunity time there. And then toward the tail end of the field, you might get under application. a lot of that depends on the cutoff point. That tends to be the point where we're looking for feedback from the field. When do we have enough advance to be able to calculate that cutoff point? And as I noted earlier, a lot of this has been done as an art for many years. A lot of excellent irrigators know that art very well, and some exercise it better than others. The lower image shows what we'd like to see from surface irrigation in terms of infiltration and application efficiency. It's the ideal, a little tougher to achieve, but with some of these tools that we're talking about, you get a lot closer to that. So one thing you need to be able to do that is control over your delivery. Steadier deliveries, higher flow rates can help depending on the soil type. If you're able to flash that water out across the field faster, you can avoid a lot of that over infiltration at the head end. But that requires sometimes changes to infrastructure, and sometimes not even possible given the amount of flow available from the supplier. Modeling, we'll talk a little more about surface irrigation modeling in another slide here, but again, we're looking for that cutoff time and a lot of different parameters in the field that we can change as well. We'll get into that a little more. Engineering and technology side. So this is what makes automation fun and sexy to sell, I guess. Automation, sensors, software, hardware, communication, whether radio, Wi-Fi, cellular, all those things. A lot more exciting to get into that sort of thing. Agronomy side, so determining how much water to apply, when to apply, the irrigation scheduling side of it, and then measuring soil moisture and that sort of thing. How much water needs to be applied to the field, if you want to accept some deficit irrigation, or indeed if you desire deficit irrigation for economic purposes. All of those factors come in here. So here is surface irrigation modeling. There are a couple older ones that I've used. I imagine there are other models. Indeed, there are some proprietary ones in the industry that seem to work fairly well also. These, you may be familiar with Windsurfer from the ARS, Surmod from Utah State, and NRCS. A little bit older models, but they do the same thing more or less. They're looking to model how water moves across the soil and how it infiltrates, and try to optimize how much gets into the root zone, how much deep percolates, how much runs off. One of those approaches is to use the advance and recession curves as a means of modeling the soil characteristics. That's one challenge, I think, with surface irrigation modeling, is the soil characteristics are dynamic. They're changing with every irrigation, indeed throughout an irrigation, especially early in the season. You may have newly planted field where your furrows or border bottoms, so forth, are very permeable, and with one irrigation that all changes. And indeed throughout the irrigation, and then as the crop grows, the hydraulic resistance changes. So it's a constantly moving target to try to understand the hydraulics of surface irrigation in the field. Some of these models take feedback from sensors throughout the field and better understand how that advance and recession curves are changing, how that affects the model. So important to understand the basics of that. I would like to encourage you folks to have a look at these models I mentioned here, Surmod and Windsurfer, because they are available in the public domain. There's great manuals on them, and a lot of the theory is available publicly as well. And as with any model, there are a lot of opportunities to get it wrong. You know, garbage in, garbage out is the mantra goes with modeling. So it's great to use these models, but keep in mind their limitations as well. Okay. May have lost my There we go. So some of the tools for automating surface irrigation, we have a sensor here from Rubicon they put downstream in the field to keep an eye on that advance, how fast it hits a certain point in the field, and can be used to dynamically determine the cutoff point. Gosh, I want to go back to that and talk a little bit about that chart there. So this is about as technical as this presentation gets in terms of equations and modeling and so forth, but you can see that a couple of the parameters that you're trying to optimize there are the depth of infiltration and the depth above the surface, and then finally that cutoff point in order to get to the desired infiltration across the field. Finally, the last point I wanted to make here on other tools to promote efficiency. So water accounting, it can be at the farm level, the field level, the basin level. Keeping track of how much water goes where, it sounds like a pretty basic concept, but you'd be surprised how little is known in actual irrigation systems and conveyance systems about where the water is going. And when we get into that water policy, like we talked about earlier, they have to make a lot of assumptions about where water is and has been historically, where there may be lack of data. So the more data that we as practitioners can gather and certify as good data, the better tools that folks who are involved in the policy side will have to then give us policies that are workable. Water balance analysis, of course, that's a very common mass balance approach to managing water. That's something that my former employer swim system specialized in, was the water balance analysis on farm. And it can be a great tool to understand from, as you see in the image there, all the different flow paths just within a field where water can enter or exit the system. And we need to quantify as much of that as we can if we intend to optimize it. So it can be a great tool to help people understand where the water is going and then be able to optimize those pathways. And say if they want to reduce how much inflow they're sending to the field, well, what happens with the water they used to be using? Would they be able to use that for other purposes or transfer it to other users? Maybe some economic impacts to that. I think that was the last slide. There are a couple of resources I'd like to mention that, I didn't get into the technical side here very much, but if you folks are interested in seeing some of the more technical aspects of this, I'd encourage you to look at the U.S. Bureau of Reclamation's Water Measurement Manual. Great resource to keep it up to date when it comes to how to measure open surface or open channel surface water. NRCS has great manuals and guidelines. ARS also has some good models. So those government approaches or resources tend to be free and open. And then online courseware, I imagine you in academia may have heard of that. There are a number of institutions who offer their lectures and lecture notes and anything aside from copyrighted textbooks publicly. And my alma mater, Utah State, has some great irrigation information on their online courseware site. There are a number of other ones that do too, so please have a look at that. And finally, thank you folks for listening today. And if you do have any questions or would like to further discussion, my contact information is there. I'd be happy to hear from you.
Thank you, Darren. Any questions for him before we wrap up here?
All right, folks. Well, thank you very much. Appreciate the opportunity today.
Yeah, thank you guys for tuning in. This wraps up our Surface Irrigation and Conveyance Systems webinar. Big thank you to Darren for leading this great session. Our next session, the Preparing Students for the Industry panel, will begin at 2 p.m. Eastern for those that are signed up for that session. As a reminder, that session has its own unique Zoom link for the panel. Thank you again, Darren, and a big thank you to our sponsor, Rainbird. Thank you, guys.